The energy of the stars has finally landed on Earth. But to understand the future, we have to look at the present. Today's nuclear power uses fission, splitting heavy atoms like uranium to release energy. It's reliable, but it leaves behind long-lived waste. Fusion is the opposite. It forces tiny hydrogen isotopes together, specifically deuterium and tritium, to create helium. This process releases 4 times more energy than fission, with no long-term radioactive footprint. In 2026, we're no longer asking if fusion will work, but how fast we can plug it into the grid. Today, we're debunking the myths with hard science.
First, is it true that fusion is always 30 years away?
Haha, not in 2026. The breakthrough is the industrialization of magnetic confinement. We have 2 main paths, the tokamak and the stellarator. The tokamak, like the massive public project ITER in France or the private Spark by CFS in Massachusetts, is easier to build but requires an internal plasma current that can lead to sudden instabilities. The stellarator, like Germany's Wendelstein 7X, is the opposite. Its twisted shape is an engineering nightmare to build, but it's naturally stable and can run continuously. Thanks to REBCO superconductors, we can now build compact tokamaks like Spark, slashing costs and accelerating development by decades, proving that the 30-year joke is finally over.
Why haven't we lit a light bulb yet if there have been records?
It's about efficiency. Q scientific is the ratio of energy produced to the energy deposited on the fuel. The National Ignition Facility hit a record 4.13 in 2025. But for the grid, we need Q wall plug. This is the net energy gain of the entire plant. While NIF and ITER proved the physics, startups like Helion Energy, which has a deal with Microsoft, are building systems designed for Q wall plug greater than 1.
Can it explode? Could it blow up like Chernobyl?
Physics says no. Fusion is self-limiting. It requires a precise triple product of density, temperature, and time. If any component fails, the plasma expands, hits the wall, and cools instantly. The reaction simply vanishes. There is zero physical possibility of a runaway meltdown.
What about the radioactive waste?
Unlike traditional fission, fusion doesn't produce plutonium, a heavy, toxic element with a half-life of 24,000 years. The only issue is neutron activation. High-speed neutrons strike the reactor walls, causing a nuclear reaction that turns stable atoms into unstable radioactive ones. However, by using low-activation materials like tungsten and Euro-1 steel, the radioactivity decays by 99% in under 100 years. This waste doesn't require a deep geological repository. It's manageable in surface facilities.
Why don't we use helium-3 from the moon like in the movies?
Helium-3 is an aneutronic dream because its fusion reaction releases energy through protons instead of neutrons. Protons can be controlled by magnetic fields and converted directly into electricity with 90% efficiency. But since it's measured in parts per billion, you'd have to process billions of pounds of regolith. For 2026, it's a long-term goal. We're sticking to Earth-based fuel for now.
Where will we get tritium if it's so rare?
Tritium is rare, less than 110 pounds on Earth. Since a plant needs more than that every year, we use a breeding blanket. This is a lining of lithium surrounding the plasma. When neutrons hit the lithium, they create new tritium, making the plant self-sufficient.
How do we keep the reactor from melting at 100 million degrees?
We use magnetic confinement. HTS magnets create a magnetic bottle so the plasma never touches the machine. The plasma-facing components, like the first wall, use tungsten, chosen for its extreme melting point. We also use diverters, high-tech exhaust systems that channel away excess heat.
Are oil companies trying to kill fusion?
No. In 2026, companies like Chevron and Shell are among the sector's top backers. They see fusion as an opportunity to pivot into clean energy, leveraging their expertise in fluid engineering and massive capital to dominate the post-fossil power market.
Will energy really be free for everyone?
No. While fuel costs are minimal, building these high-tech plants is expensive. It won't be too cheap to meter, but it will be a stable, carbon-free baseload that prevents the price spikes of fossil fuels.
Can we use it to go to Mars? Yes.
Startups like Pulsar Fusion are planning orbital tests by 2027. By using the immense exhaust velocity of fusion reactions, we could cut the trip to Mars from 6 months down to less than 3. This makes deep space travel not just a possibility, but a sustainable reality. Fusion in 2026 is an industrial roadmap. It will be the bedrock of our 2040 energy grid, powering everything from AI data centers to heavy industry. The point of no return has been reached.